Hello there, and welcome to ie537 Large-Scale Systems. We're going to continue in the spirit of having experts, subject matter experts, tell us about technologies, in particular modeling and analysis tools that are useful for large-scale systems analysis. And in that spirit, today we're getting into intelligent agents. And we're fortunate to have with us today two what I consider to be world-class experts in intelligent agents. One is Shannon Spires, the other is Stephen Goldsmith. I just want to say a few words about their credentials. First of all, Mr. Spires joined Sandia National Laboratories in 1986. He's the chief developer of several technologies in Sandia's Advanced Information Systems Laboratory, including the HOTE, HOTBAC, and the Spire Store Object-Oriented Database. He is the author of several papers in the field of multi-agent systems, agent-based research, and object-oriented databases. His primary research focus is large-scale data mining with multi-agent systems. Mr. Spires received a bachelor's in electrical engineering and a master's in electrical computer engineering from the University of Texas. And Shannon holds 2 patents. Our other guest worked very closely with Shannon, has for years now, is Dr. Stephen York Goldsmith. Dr. Goldsmith is a distinguished member of the technical staff at Sandia National Laboratories in Albuquerque. He received an MSEE in 1979 and a PhD in engineering in 1989, both from the University of New Mexico. Since joining Sandia in 1979, he's developed information and control systems for a broad selection of application areas, including particle beam fusion accelerators, intelligent signal processing, seismic monitoring, arms control and tree verification, cryptography, environmental life cycle analysis, e-commerce, robotics, and cybersecurity. Since 1995, Dr. Goldsmith has focused his research efforts on intelligent agent systems and technology, particularly in the area of adaptive software architectures. His current assignments involve the application of intelligent agents and multi-agent systems to advanced cyber systems and distributed energy management problems. Dr. Goldsmith has published numerous papers and presentations and has received 4 patents. Just another word about the slightly, I guess, different intellectual content in this next series of 3 lectures. The last series that we had was focused on the SOSAT, as you remember, the Systems of Systems Analysis tool set. And you were shown the software, but you're not provided with it for various reasons, largely having to do with how to transfer the intellectual property. We're shifting that here in this next series. You're going to be actually provided with software, and I believe what you're going to see is in the homework an example where you're going to be able to exercise the software. The other thing I'm particularly excited about with this one, as I mentioned to you in previous lectures, one of the things that came out of our System of Systems colloquium we had last summer was that there was no good way for modelers and analysts in these complex adaptive System of Systems venues to federate different models. Federate being have them talk to one another and be on the same page, essentially. That was one of the profound challenges, and in fact that was given to the National Science Foundation to put on their research agenda. One of the things I've been pointed toward for this next module we have coming up, the 3rd and final module, is in your class project. I want to get into how we explore federating these various modeling and analysis tools. Later today, or I believe, in the 3rd lecture in this series, I believe you're going to be exposed to a methodological approach to this federation with an intelligent agent essentially federated with the systems dynamics capability. So I'm excited about seeing that, and that'll give you an opportunity to see how one explores, anyway, this federation approach. With that, let me introduce again Dr. Goldsmith, who's going to begin the lectures on intelligent agents. Steve? Pass the lavalier baton here.
Okay, so Dennis asked Shannon and I to talk about agent-based modeling and simulation, and I think the qualifier there is for large-scale systems. So really, there's two aspects that are important. First is the techniques and technology associated with agent-based modeling and simulation, and then the issue of scalability. Do these models and simulation techniques work for systems, very large systems, as they scale up? So we'll try and address both issues. So the syllabus of this course is really in three parts. The first thing that we want to cover is an introduction to agent-based modeling and simulation. So we've got to cover the motivation behind agent-based modeling and simulation. Why did the technique arise? Well, what is it good for? Why is it important? And then there are some basic concepts associated with agent-based modeling and simulation, some terminology that distinguish the kinds of systems you model with ABMS. There are certain concerns that you have to address when you use ABMS, things like scale-up, et cetera, et cetera. ABMS has been applied to a lot of different domains, so we'll cover briefly a representation of the different fields. We'll look at some selected toolkits, not in much detail, and then we'll discuss the readings assignment. In the second half, we'll get into a little more nuts and bolts of the design and analysis of an agent-based modeling system and simulation system. We cover agents, the environments that the agents inhabit, the behaviors that the agents exhibit, their crucial interactions with one another, and the kind of measurements that you typically take to evaluate your simulation. Now, throughout this phase, we'll touch on aspects of the homework problem, continuing with with Dennis's problem of the neo-Luddite insurgency. Prior to that, we'll look at a couple of example models, and then Shannon Spires will give you the homework assignment and explain the system that we use to model the neo-Luddite insurgency. Okay, so by way of introduction, there's a couple of questions we have to answer first. What's distinct about agent-based modeling and simulation? Well, it is a technique for modeling and simulating dynamical systems. So we're concerned with the behavior of systems over time and space. ABMS is also a technology for modeling and simulating dynamical systems. There are toolkits, there are approaches to representing the model, there are techniques for improving the performance of the simulation. So there is a substantial amount of technology available to you to do ABMS. So what distinguishes ABMS is the primary abstraction. The primary abstraction is called an agent, which is an individual element represented by some software structure. And the choice of software structure generally distinguishes the kind of simulation that you're going to run. Now, the primary substrate or environment is usually some form of network or lattice. So we have agents inhabiting an environment or a world that's represented as a 2D, 3D lattice or some arbitrary network. Now, when you run the simulations, the primary computation is to determine the effects of agent interactions with its environment, non-agent objects, or with other agents in the environment. So there is a notion of sampling or a loop primary loop that these programs execute. Now, the primary data produced by an ABMS is usually some sort of global average or statistic, or measurements on agents' populations, the fitness of a particular subpopulation of agents, some quality of either agents or the environment, power measurement. There's a variety of kinds of measurements that you want to take. So the next question, and the most dreaded question for any agent researcher, is what is an agent? So the term agent has been misused, abused, and over-applied in many different ways, probably to the point where the semantics are really questionable. So you really have to take time to basically take time to say what you mean by agent in general, and in particular what an agent is in the application that you're representing. But we'll take a shot at giving very general definitions of an agent, basically things that probably aren't too controversial. So the one I like the best is that consider an agent a locus of sensing, decision, and action with respect to some externality, other agents or objects in the environment. So an agent will execute some sort of sense, decide, act loop and exhibit behaviors and influence its environment through that loop. An agent can be considered an individual element that's distinct from all other individuals or objects. So the notion of identity and distinction is very important with this primary abstraction, the agent. The term often applied to agents is autonomy. So most of the time we consider an agent autonomous with respect to its decisions and its actions. Another property assigned to agents is goal-directedness. An agent is purposeful in its existence. It has some well-understood role to play in its environment that goes along with its identity. To make things interesting, agents must be coupled through some causal relationship with other agents or objects in the environment. This coupling and interaction among agents and objects is essential to the simulation. And agents are usually considered imbued with some form of intelligence. Now, the term intelligence, again, is questionable. The definition of intelligence has defied the artificial intelligence and cognitive science community for a long time. It usually devolves into a philosophical discussion. But I think most people have an intuitive sense of what intelligent behavior consists of in a particular environment or application. So you'll just have to trust your intuition on that. So another fundamental question, again, is when to use an agent-based simulation to model systems dynamics. There are many different approaches. Traditional approaches have been used for years in engineering and in modeling, based on traditional ordinary differential equations or partial differential equations, the so-called traditional methods. So in general, an agent-based simulation may be used when, for some reason, because of scale, perhaps the problem cannot be solved by traditional methods. Another one is when the problem structure is poorly understood. And this is a primary use of agent-based modeling. When you have to do exploratory modeling to begin to understand the system and slowly uncover the parameters, the behaviors, and the structure of the system, agent-based modeling is a good technique for exploratory analysis of these kinds of systems. Another good one is when there's uncertain or incomplete information. about the system or its environment. Again, in the exploratory mode, you can begin to uncover the relationships, the noise in the system, the lack of information or detail that you might need to represent the system in a sort of an iterative fashion. Sometimes an agent format is natural for the existing information you have on the system. So if the information on behaviors, for example, is already allocated to some notion of an agent, then the data and parameters are captured in an agent-friendly format. So this is a natural reason to use an agent-based approach. And again, when the agents are an obvious and natural representation of the system, the agent objects apply to people or distinct entities like robots, vehicles, other machines, biological organisms. Those are all tend to be very naturally represented by an agent-based approach to modeling. Another one is when the system is naturally distributed. In general, the underlying structure of an agent-based simulation is as a distributed system. So you have multiple agents interacting with one another, communicating or influencing one another in a distributed fashion. One that actually occurs quite often is when you have non-technical experts, that is, non-computer scientists, say perhaps sociologists or biologists in a particular domain, that really want to quickly create a system model and explore some of the topical aspects of the model. The agent-based modeling and simulation toolkits generally support some rapid prototyping and development that help the expert quickly capture the essential aspects of the system. And then last but not least, sort of the mother of all reasons, when the system is too complex. That is, the system is a so-called complex adaptive system. So we'll get into definitions of what a complex adaptive system is in just a second. How did agent-based modeling and simulation arise? This might be a little controversial, but in my experience, it's generally credited to the Santa Fe Institute circa 1989. Researchers like John Holland and Stuart Kaufman were beginning to explore the notion of complex systems in general, and naturally computer tools to represent those systems began to arise about those times. The initial systems and development toolkits appeared throughout the 1990s, basically. And as computer technology and network understanding improved through the 90s, so did the toolkits. In my opinion, real maturation in agent-based modeling and simulation occurred between 2000 and 2006. During those years, you saw agent-based modeling and simulation adopted by many organizations. Fairly complex simulations were attempted. Research publications flourished, and in general, the field by 2006 was pretty much widely accepted. Mainstream technology occurred in 2007. So here we have traditional engineering organizations adopting agent-based modeling and simulation as a valid technique to understand the various domains that they were working in. It's probably only fair to represent molecular dynamics models based on particle systems. The physics world had adopted particle-based models fairly early, and so some of the technology and some of the techniques were influenced by those early physics models. Okay, so along with the technology and term agent-based modeling systems, there's generally a notion of the kinds of systems that it represents. So there's a lore and a field of knowledge, if you will, that underlies agent-based modeling systems. And one of the terms that really have to begin to explain but is very elusive is the term complexity. So this concept term is applied to the system as a whole. So it basically indicates that you have a particular system on your hands which is not easy to analyze or understand. In other words, you cannot produce an analytic solution for its behavior based on its parameters. Usually it's the term nonlinear, sometimes stochastic is applied. And generally it's assumed that a complex system is composed of many different and variously connected parts. So you have many different elements, you have many different types of elements, and you have many modes of interaction among those elements. So that's about as far as anybody's willing to go in terms of complexity. There's an awful lot of philosophy associated with complexity. It's beyond the scope of what we're talking about today. And in general, metrics for complexity have been not forthcoming. It's difficult to compare the complexity of two different systems. But it leads us into the term complex adaptive system, which most people have heard before. A complex adaptive system is a kind of complex system that exhibits complexity that alters its structure and its behavior over time. So the notion is that in some sense the character of the system changes over time. A complex adaptive system is one that may learn from its historical operations and interactions. So in some sense it has memory and it has some means of analyzing or incorporating historical performance, that is, its interactions with its environment over time, and improving its behavior. Another definition is a system composed of components with very intricate kinds of causal relations, multiple feedback loops among many different elements at many different levels of organization. And finally, another approach to defining complex adaptive system is an integrated whole, a holistic approach, a system that maintains its organization and its function over time and throughout changes in its environment. So the notion of a complex adaptive system changing its structure and behavior to suit changing conditions in its environment is the essential concept. Okay, another important term of art that's a difficult one for many people is the term emergent property, or the concept of emergence itself. We'll stick with trying to define it in terms of properties of the system because that's most useful for crafting and evaluating a simulation. So this is a term applied to the system as a whole. Basically, an emergent property is a property that appears in the whole as a result of the interactions of its parts. That's a simple or weak definition of an emergent property. In other words, it's a global property, a set of measurements or phenomenon that exist when you view the system as a whole, but necessarily resulting from the interactions of its parts. Another definition is an emergent property is a property of the system that is incommensurable with the property of the individual parts. So in some sense, the emergent property units or measurement does not relate to the units or measurements of its individual parts. So through the interaction, somehow the idea is a new kind of property or phenomenon has arisen in the system. Along the same lines, an emergent property is a property of the system that It can't be traced to the properties of the components, but again necessarily arises from very numerous synergistic interactions of its components. Another term that you'll hear is supervenience. So an emergent property of the system is a property that supervenes on the properties of its components. I suggest that you look up supervenience and investigate it yourself. But in general, the notion is that the global properties of the system may actually influence the properties of the individual components in ways that are difficult to understand. So this is so-called downward causation. And again, this is a philosophical issue of great debate in the theoretical community, but I think it's worthwhile to investigate it, but through the web or through a wiki or other definitions. And again, another important aspect that is somewhat the debate of philosophers is emergent properties defy the approach of reductionism. Reductionism basically is a technique that we all inherently use as engineers and scientists that says that we understand the phenomenon of the world by reducing it to individual parts in sort of a layered or hierarchical fashion. So as we peel the layers of the onion away, we assume that we can basically describe the phenomenon that we're talking about by describing the phenomenon of the parts. And then the summary of this is the whole is greater than the sum of the parts. So another concept term is self-organization. And this is a term applied to the system as a whole again. Generally, self-organization is a process through which the system arrives at its structure without any external intervention. That's intuitively, that's an intuitive definition. Another one is a process in which the internal organization of the system increases in complexity without being guided or managed by an outside source. So the notion here is that through its own devices and volition, this holistic system can produce increased complexity in its organization, that is, its components, the interaction between its components, and their behaviors with respect to the environment. Necessarily, a self-organizing system is going to change its global structure in response to changes in the environment. So the notion here is that throughout its life history, the system will undergo significant changes in structure and or behavior as its environment changes. Generally, self-organization is considered to involve feedback, both positive and negative, at many different levels in the system, and exhibit exploration and exploitation. So exploration in a system is a notion that it samples its environment and uses that information to learn new behaviors. Exploitation is, in a system, is the notion that learned structures are somehow efficient and provide important interactions with the environment. So generally there's a trade-off between exploration and exploitation. The more a system explores, the more mistakes it makes, and its performance is poorer. And the more the system exploits learned structures, the better its performance. So this is a direct trade-off. And self-organizing systems are generally considered open systems. And an open system is one that exchanges matter, information, or energy with its environment. In other words, there's flows in and out of the system as opposed to a tightly contained system that does not interact outside of the environment. Another important concept is that of a critical point. This term is applied to the parameters or state variables of your system. And in general, a critical point is a parameter or a point in state space at which the system undergoes a phase change. The term phase change originated with the field of physical chemistry to describe the temperature, pressure, volume parameters associated with a liquid moving to the solid phase or a liquid moving to the vapor phase. And it's represented as a point in the state space, if you will, of the macroscopic system, that is the matter as a whole, and not in terms of the individual energies and interactions of the molecules. In the context of modern systems, phase change has been broadened to indicate basically a parameter or state vector at which the system's emergent properties will change abruptly in relation to the previous state. So we try to capture some notion of significant qualitative and quantitative change in the behavior of the system at a particular critical point. Generally, these systems are nonlinear and random or stochastic to exhibit the phase change property. Along the same lines, you'll hear the term self-organizing criticality. This is a term applied to a critical point in the system. And a self-organizing criticality is a critical point of a system that is also an attractor. Now, an attractor in a system is a stable region of the state space that a system will remain within, and its trajectories will be bounded by over time. So it's a well or a sink that holds the system within its boundaries. So the important notion here is that there is an attractor that the system will tend towards, but it's also a critical point. So the system will tend towards a critical point at which it can move very rapidly from either a previous state to a new state through a phase change. So this results in critical behaviors that are basically insensitive to system parameters. Since the attractor pulls the system into its region, these systems tend to operate naturally at these critical points. And again, these are generally open systems that are not in equilibrium. Equilibrium being some form of steady state exchange in which the behavior of the system is assured to be constant. Okay, another important concept that's a subject of a lot of research right now is the term self-star. This is a term applied to the system and its components or agents. Self-star properties are anything like self-organizing, of course, self-assembling, self-understanding, etc., etc. You can have a lot of fun with these terms, trying to understand the behavior of your system with respect to self. So what's important here is definition of the self. Basically, the entity is the essential being that distinguishes it from others. Basically, it's considered as an object of introspection or reflective action. So there's a distinction or boundary. In our case, we're going to talk about either an individual agent abstraction, or we're going to talk about a macroscopic view of the system as a whole. So it's really important to identify the self and non-self boundary and really understand what the individual is at the particular group, class, or family level. In general, systems may have many different levels of organization that aggregate different components, and at each level you may consider an aggregation as an individual. The important thing is it's a property or behavior assigned to a distinct entity in the system. So self-star, again, is a new idea, and along those lines I have a long laundry list of self-star properties to examine when I go through a simulation, basically trying to map the common notions of what self-star is to a particular behavior or aspect of autonomous agents. So here are a few of them, and there's many others. But in particular, important ones would be a self-aware system. This is a system that's capable of introspection. It has some notion of understanding its internal structure. It has some meta layer of behavior and control that can monitor and alter its internal structure. Self-controlled. This is a pretty easily understood concept to be mapped to in autonomous agents. An agent that's self-controlled somehow has boundaries and limits associated with behavioral parameters. Self-creating, a system that can, an agent system that can reproduce itself. Individuals are reproduced or structures are reproduced. So you can have a lot of fun with this approach. And basically, what I do is I go down this laundry list, and on the left-hand column, you have to interpret what these things may mean, if they're even relevant, all relevant to your system, in the context of your application. This helps clarify the thinking a bit. Okay, another concept, autonomy. Autonomy is a big issue in the agent community. Again, it's a term that's somewhat elusive, but you know it when you see it, or at least you're comfortable with saying your system is autonomous when you've built it. Generally, it's applied to a component. Autonomous means self-determined or independent. So in our case, our decisions, our agent decisions for autonomous agents are going to be based on sensory information, decision patterns, and past behaviors. It does not mean that the agent is impervious to influence from the outside world. It wouldn't be very useful if it didn't have interactions and exchanges with the outside world. But the notion is that it has its own approach, it has its own role and identity, and it behaves according to its own internal programs and patterns. The term adaptive is also applied to both system and components. A definition is to become adjusted to new conditions. The idea here is the agents must improve their performance somehow based on experience or interactions with one another in the environment. In other words, it's learning and possibly at various levels of the system. So you could have systems that learn on the individual basis at the lowest level of granularity. You could have systems that learn at the level of different aggregations in the systems, or the system as a whole could exhibit some learning behavior, hence complex adaptive systems. Another concept usually applied to timing relationships among components is asynchrony. An asynchronous system is basically pertains to processes that do not depend on the occurrence of specific events, particularly common timing signals. Property of an event that occurs in an arbitrary time without synchronization. So agents in a complex system are necessarily asynchronous in their actions. There's too many of them to synchronize to have a master clock. There isn't essentially no overarching controller that could provide a synchronizing clock to these systems. But there is an interesting counterexample. Some complex systems can exhibit induced synchronization as an emergent phenomenon, that is, through local interactions and spreading activation, if you will. The system as a whole may exhibit some synchronized or clock behavior. Okay, so those are the essential concepts, about all we have time to go into for a two-lecture series. I urge you to use the web and investigate these terms. There's a lot of information about those terms. Make yourself comfortable with them because they basically inform your conversations with your colleagues about agent-based modeling system, and they'll also inform you in terms of constructing your agent-based simulations. Now, there are a set of concerns associated with doing agent-based modeling and simulation, not the least of which is scale effects. The concept here is that the system changes its behavior at certain scales, but because of its complexity, you don't know what scales you'll see these changes in behavior. In particular, you can have something like drastic transitions, phase transitions, if you will, when the system grows to a certain number of elements, the behavior is qualitatively different and changes very, very rapidly as the system grows. Another aspect of scale effects for network systems is that the system behavior depends on the distribution of links or connections among agents, or the dimension of the space, 2 space to 3 space. So there's a few examples of system changes based on the number of links and the distribution of the links, the number of nodes. In particular, for so-called dynamic networks, which is a topic that is related to what we're talking about. Networks that grow, that have particular distributions among their links, and exhibit these changes in behavior. So these are generally called monotone properties. They can change abruptly in a small range of parameter values, and hence may not be obvious at at particular scale or level of simulation. So what it causes you to have to consider is doing studies, scale-up studies, informed by some theoretical aspects of the graphs or networks you're working with, to make sure that you see the phenomena of the system as it grows. Most of the theoretical results are based on infinite-sized graphs with particular well-described distributions of links. So a big issue is how many simulations at what level and what scale do you have to do to make sure you've captured the important aspect of changes in the behavior of the system. So, and also results at one scale may not relate to results at another scale. If you scale up the system, if you do a simulation at one scale with a certain number of agents and actors with certain levels of interactions, you really may not be able to guarantee that that's the behavior that you'll see when you increase the size of the system. Another concern, sort of a more practical one, is that the objectives of agent-based mod sim have to be carefully defined. Generally, it's assumed that for complex adaptive systems, simulation is really the only means of understanding system behavior. That's not to say that there isn't an awful lot of theory that can be applied, the concepts we discussed, and even mathematical techniques. But in general, there's no closed-form solution for the trajectories of the system given certain inputs over time and space. So simulation is essential. Given that, there's really two issues in the kind of simulation and objectives that you have. One is you're trying to produce a facsimile of an existing system. In other words, you expect the model and the simulation that you run to exercise the model to faithfully represent some large-scale system that you're modeling. The other approach is that you're building an exploratory simulation. You may not expect the exact results of your simulation to represent behaviors you see in the real system, but by modeling and simulation, you are able to discover important relationships, qualitative and quantitative, aspects of the system that you didn't know were there. So it's very much a rapid prototyping or exploratory kind of activity. Currently, the holy grail of agent-based mod sim would be to produce predictive models. That is, perhaps facsimile models that are able to give indications and warnings or otherwise alert operators or people that systems are about to undergo a phase change or some other radical and important event is about to occur. These models are very difficult and currently beyond the scope of current technology, with a few exceptions. But in general, large-scale, complex adaptive system models are not predictive. Descriptive models is somewhat easier. You're merely trying to validate or capture the behavior of an existing system. You may have data, you may not. big issue is verification and validation. Verification and validation are open issues. You may or may not have enough data of enough quality to put into your simulation to reconcile it with reality, with the fact, with the real system. So this is a big open area, and currently some research is being done in this area. And sort of summing this up, if there are certainly in the government and industry folks who have funded simulations, complex adaptive systems, large-scale simulations, and hence their expectations were not managed, and hence they're somewhat skeptical of the value of these simulations and the data that they produce. Finally, there are always issues of tractability and performance. You have to be careful that the problem that you're representing is computationally tractable. It's not a wicked problem, that there's enough information to represent it, that you're not violating some basic laws of computer science. Asymptotic complexity is understood. Then, more practically, do you have enough memory to run your simulation? Depending on how you represent the system, it may be memory intensive. Another issue is how long do you have to run the simulation to achieve mixing? This is particular for Monte Carlo stochastic-based simulations. There's a certain essential amount of time, usually unknown, it's a parameter of the system that you have to run to get good quality data and to observe the phenomenon over a long enough period to make at least qualitative judgments about the behavior of the system. And finally, you may require parallel or distributed computing to run the simulation. It may be of that size and complexity. But these require that you have modeled your system and your simulation with the proper architecture that supports parallel or distributed computing. Okay. So the agent-based modeling and simulation has been applied to many different application domains. Some are more successful than others, but we'll just go over a sampling of these. In biology, complex adaptive systems represent genetic networks, the transfer of information among genetic networks. Metabolic networks, the transfer of energy within cells. And probably most common, they represent ecological systems. That is, systems of different organisms functioning in a common environment under constraints. Their effects on one another. The simple example would be a predator-prey example. Currently, there's a trend to model social networks. That is, people interacting with other people, their relationships, their effect on one another, how societies and cultures function are currently modeled by agent-based techniques. Another good one is crowds, the effects of crowd behavior, which is generally distinct from individual behavior. Here we see something like emergent properties, that is, the behavior of individuals will be affected by the holistic system and may induce behaviors that are different than they would normally be given a smaller crowd or a single individual. We've seen a lot of activity in modeling terrorist cells with social networks. In the area of military systems, certainly complex command and control systems have been modeled with with agent techniques. I know of simulations for small force engagements and other levels of warfighting that use agent-based techniques to represent the behaviors of individual soldiers, vehicles, units like squads, up to battalions and so on and so forth. So various levels of aggregation. Agent-based techniques have a long history in economics. The holy grail among a lot of people is to capture the dynamics of the stock market, which which of course is a system that's influenced by the individual decisions and behaviors of the people investing in the stock market. Capital flow on a macroeconomic sense is another one that has been modeled with agents representing institutions, banks, or countries for international trade. And also microeconomic behavior, where the agent is an individual making a decision based on supply and demand. The field of engineering, collective robotics, is currently an important field that's being modeled with agent-based techniques. Interactions of robot teams for say, military purposes or search and rescue, cooperative manufacturing systems are another one. And also operations models, that is, complex organizations consisting of people, machines, information systems, such as space mission operations. The field of information systems, cybersecurity is a big one. We are modeling cybersecurity and defensive systems using agent techniques. But also in general, distributed systems. Distributed control systems are an important application. We are also looking at modeling distributed energy systems and the control of distributed energy systems using intelligent agents. And finally, business, again, operations, but a big one that's been investigated is supply chain dynamics. How do you model supply chains for just-in-time delivery, to reduce inventory, to ensure manufacturing capacity, et cetera, et cetera. Okay, just as an aside, I think since this is a web-based course, we're really trying to focus on enabling you to do the exploration, the homework and background work through the web. So being from a national lab, I'm going to point you to 3 websites. These are DOE national laboratories that have an awful lot to offer if you'll take the time to browse these and understand what the organization does, look at their sampling of their publications, what tools they have, conferences, et cetera, people, et cetera. Argonne National Laboratories, the Center for Complex Adaptive Agent System Simulation, is a major player in the area. They have a lot of experts there. They have tool sets. They publish significantly. They model a variety of systems. Here at Sandia, the National Infrastructure Simulation Analysis Center, so-called NESAC, which is cooperative with other national labs, including Los Alamos, is a premier site to understand how modeling and simulation applies to the notion of complex interconnected infrastructures. It's a very important area for security reasons. The idea is that our communications, our national communications network, is closely coupled to our internet, which is closely coupled to transportation, energy, fuel, water, et cetera, et cetera. In other words, interconnected systems of systems. Trying to understand the behavior of the system as a whole, the viability, if you will, of our national infrastructure, given effects that occur in one system and that ripple through to affect other elements or systems in the infrastructure. And last but not least, Los Alamos National Laboratory Center for Nonlinear Studies, over many years, and sometimes in collaboration with Santa Fe Institute, sometimes not, is really a science and mathematical center for understanding complex adaptive systems. They've been doing this for many, many years, and generally this is where you go to see the highly theoretical and mathematical research on complex adaptive systems or agent-based modeling. Now, there's a lot of development tools out there, various levels of complexity and sophistication. Basically, what I'm going to give you here is a small sampling of tools that I think are worth investigating first. Since the majority of modeling and simulation activity and maturation occurred from 2000 to the present, we're going to look at fairly modern toolkits. Over the years, papers have been published on sort of small or idiosyncratic toolkits or approaches, homegrown toolkits that were put together for the purpose of a particular piece of research. We want to focus on tools that are general purpose. Many of the tools are open source, which is good, but they require different levels of programming skill. Some require you to program in traditional languages, object-oriented languages like C++, Objective-C, Java. And then the other issue is whether the tools are suitable for large-scale simulations. And when you want to go to large-scale simulation with many actors and complex performance, it sort of weeds out a lot of the tools. And so toolkits for large-scale simulations are scarce. I think that may be, other researchers who produce toolkits may argue with that. But in general, when you go to large scale, our approach is to look at homegrown solutions. So we also want to make sure that the tools we recommend or look at are currently in use by experts and have some sort of support by institutions. And also are used in current publications. So this gives you some confidence that the toolkit is currently viable, that it's maintained, that it's advancing, and that if you invest the time to construct a simulation in this tool, that it's not going to be obsolete anytime soon. So along those lines, we've chosen tools produced by large organizations, NASA, Argonne, Santa Fe Institute, and Northwestern University. And again, scalability is still an open issue. A lot of the toolkits, well, a toolkit really requires some architecting for multiprocessing or parallel processing or cluster computing, and it has to have features that support the partitioning and allocation of agents and elements of the environment across multiple processors. So if you want to have a scalable toolkit, you're going to have to ask the hard question about how the toolkit basically supports that activity. And in order to support scalability, again, because the simulations are difficult, expensive, you want toolkits that are mature, productive, and supported. In other words, have a good pedigree. Okay, so the first tool is called BROMS. It's produced by NASA. Basically, BROMS is used for modeling integrated work processes involving humans, robots, computer systems. So it's primarily used for modeling space exploration and mission operations. Because it's NASA produced and it has a pretty good pedigree and maturity, I presume it's supported, but it's not open source as far as I know at this time. So there's a URL that you can search that gives you a brief summary, and you can go ahead and, in the spirit of this web-based course, search the web and find various pieces of information on this toolkit. The next toolkit is REPAST, Argonne National Laboratory. This is an open source toolkit. It's under SourceForge. And it's developed by experts at Argonne National Laboratory. They publish a lot. They have a serious commitment to modeling complex adaptive systems. So it has a good pedigree and maturity. Basically, it's based on a modern Java development environment, and it's currently viable. There was a tutorial offered at one of the big agent modeling and simulation conferences just last year. So it appears to be a good candidate. You can receive training and participate in the open source development. So there are a couple of URLs here, several URLs. pointing you to the code itself and the tutorials. Swarm is a toolkit that's been around for a long time. Originated at the Santa Fe Institute, but it has been taken over by a private organization called the Swarm Development Group. This is an open source toolkit. It's got a large user base. There's a dedicated development forum, lots of people interacting, discussing their use of the toolkit. It has a fairly long history. It's one of the original agent-based modeling and development environments, circa 1996. And development in Swarm basically occurs in Objective-C or the Java language environment. So this is a very popular one. We have the whole home page, and you can download software from the sites listed there. And last but not least, NetLogo, which is supported by Northwestern University. It's another freeware tool. Has a significant, subscriber base and that contributes different models. It has a library of many executable models. And it's supported by Northwestern University Center for Connected Learning, computer-based modeling. So, it's supported by a major university organization. It has a long history of use, a good pedigree. It's distinguished by the fact that it has a fairly intuitive and straightforward development language based on a set of abstractions. So it's not a formal computer language such as Java or C++. But this is a very popular language and or system, and again, a tutorial was offered at a major conference in 2007, so it appears to be viable. This particular tool set is used in the homework problem by Shannon Spires. So he's going to lead you through the use of this environment, and you'll have to download it and do the homework exercise. Finally, we should address some issues about when you should roll your own agent toolkit, and this is going to be a matter of opinion. In general, you may find, if you have a novel domain, that the features that you need are not supported. We found this to be true in software, open source software for Monte Carlo and Markov chain that is stochastic simulation models. So not every technique is going to be represented. You may have to roll your own when scale up for large-scale systems require some innovative representational techniques or memory management. In other words, you have to highly optimize the structure of your program to squeeze every bit of memory and representation that you can. Along the same lines, you may have performance requirements that require innovative optimization of algorithms, or even special purpose techniques, trying to adjust the runtime of your system so that you can conduct simulations in a reasonable amount of time. Another one is that in a lot of cases, the researchers are also good programmers. So if you have a very rudimentary toolkit for simulation in a programming language, it may actually be more efficient for the researchers to write their simulations directly, and that way they have mastery over the software and the code, and there's really no mystery about what algorithms are functioning, easier to debug and validate to some extent. Another reason may be that simulation code requires parallel or distributed computing platforms. As I mentioned earlier, you may actually have to craft your simulation code properly to be able to take advantage of parallel or distributed computing platforms. Many toolkits don't support that. Another reason may be that you have a long-standing modeling activity that's single purpose, that's heavily funded and will be funded, and rather than make the connection to an existing open source toolkit whose evolution and support is may be questionable, you may want to undertake to develop your own internal simulation and modeling environment and spend the money to have programmers and engineers maintain it and keep it viable for the duration of your activity. A related reason would be you have a sensitive and classified domain, so that you have structures that you don't want released or shared in the open source. And in general, no single toolkit is going to have address all of the above. So it's conceivable you could start out with a quick and dirty, if you will, simulation in one of the existing toolkits and rapidly find out that you have to begin to roll your own to really explore the aspects of the system that you need to. Okay, so we have a reading list. It's a modest one, and there's an awful lot of papers out there that we could reference. And so I want to give you the reason why we selected the ones we are. First, they have to be informative, somewhat tutorial in style, or they have to illustrate some sort of agent-based modeling theme that we're stressing in the lectures. Some of these papers address issues that we're going to discuss in the next lecture and that Mr. Spires will discuss when you get into the actual nuts and bolts of the simulation. I wanted current papers. I wanted papers that have been published since about 2002. That seems to be a lot of those papers. I didn't really want to go back to the early 90s or mid 90s or even late 90s. Papers have to be accessible, so all the papers are available for download on the World Wide Web. We wanted them to be readable, so they're not full of domain-specific jargon or addressing a particular domain audience, such as sociology or biology. And finally, we're going to keep this reasonable. So I've really just listed 4 required papers, and then gave you 2 optional papers and a book. Okay, so the first set of papers are really companion papers produced by Argonne National Laboratory. These are authored by experts, and I think they're probably the best set of introductory tutorial papers that I've found. So both of those are fairly current, 2005 and 2006. It's a series. The next paper is important. It's authored by a NASA team. It discusses the Brahms tool. By the way, the previous papers discussed somewhat the repass toolkit. The interesting thing about this NASA paper is that it basically models space mission operations involving humans, robots, computer systems, and space vehicles. So it illustrates the flexibility of agent-based modeling systems to represent different types of agents in a complex environment. So it's a multi-type simulation. The operations expressed are real. They're important planning tools for International Space Station missions and missions to Mars, et cetera, et cetera. So they're serious kinds of applications. The final paper is one that I found that I think is interesting. It covers a number of general aspects and practical considerations of doing the agent-based models. He does a good job of covering the themes of how to model and what the issues are. That's a good one to orient yourself in preparation for the exercise using NetLogo. A couple of optional papers. One from biology. This is a very informative paper in a general sense that discusses agent-based modeling in general. They tend to explain terms and so on, but also introduces work on agent-based modeling of biological processes. So that's optional, but I think it's worth reading. And finally, one from economics that's rather unique, but again informative. It's a specialized paper describing a network for transfer of funds among banks. This is a simulation that was done here at Sandia under NESAC. It's atypical of economics models in that it's not following any economic theory in macroeconomics, but it is a practical one that it illustrates the dynamics of transfer of funds among banks, and it also is representative of modern dynamic network theory and agent-based modeling, so-called random networks, small world networks, or scale-free networks, which is an underlying area of research. And I'm going to give you one optional book to read. There are many good ones. One that I like that is fairly broad and has some seminal results in it is The Complexity of Cooperation by Axelrod, University of Michigan. He discusses agent-based models of competition and collaboration. So I'm going to give you a good feel for some of the interaction dynamics among agents. In particular, he has some evolutionary models of social norms and produces a very important model called the prisoner's dilemma and iterated prisoner's dilemma. I think this book is well worth reading. Again, there are many others. I'm just going to suggest one. Now, as the next section of the lecture will address practical aspects of modeling in SIM. How do you build models? What are the concerns? How do you represent agents? And we'll be giving you an example from the area of cyber defense as a teaser. And also, we'll be discussing and developing the Neo-Luddite insurgency representation that was the subject of the homework. So that concludes this lecture. So next time we'll dive into more practical matters, give you some techniques for thinking about models and developing your simulations.